This is going to be a short video on our measuring the length of a microwave lab. Let's have a look at it. So this graphic here kind of draws your attention to the visible spectrum, but we're not thinking about the visible spectrum. We're thinking about electromagnetic radiation that is in the longer wavelengths in the visible spectrum. In particular, things that are about millimeters long up to about 10 meters long. Those are microwaves. And microwaves are chosen because they are used in a microwave oven to excite water molecules, in particular, to heat them up. They transfer energy from the microwave to the water molecule, and that's how a microwave oven works. Because microwaves are in the length of anywhere from the millimeters to meters long, that makes them waves that we can actually, if we could detect them in some way, we could actually measure their length with a ruler, and that's what we're going to do. So for our supplies, we need a microwave to start with, and most microwaves have a frequency of 2.45 gigahertz, or a gigahertz is 1 to the 10 to the 9 times 10 to the 9 hertz. So that would be 2.45 times 10 to the 9 hertz. Those are obviously outside of the visible range. You see them as hot spots on the thermal paper. So let's have a look and see how we're going to set this up. The way a microwave works is that it has certain hot spots. And in order to just avoid heating certain parts of the food that's in there, you have a tray that sits in a microwave that spins, and that rotates the food in and out of those hot spots. So for example, the hot spots demonstrated here would be at the points of the highest amplitude, here and here and here and here. And so the entire wave is from peak to peak or from valley to valley, either way. You can measure the length of it. But of course, because it has hot spots both in the valley and the peak, we're going to measure between two hot spots and then multiply that by 2 to give us the length of the entire microwave. The way we're going to set this up is we're going to take a piece of cardboard, something that will fit easily inside the microwave. Matter of fact, we'll cut a piece of cardboard that's basically the same size as the plate that's in there. We are not going to have that plate turn, however, so we're going to put the cardboard up above the spinning mechanism there. And onto that cardboard, we're going to tape some thermal paper. The thermal paper is designed that where it gets hot, it turns black. And so we're going to tape some thermal papers to it. And then we're going to turn the microwave on for about 20 seconds. And we should see black spots where you have the intensity at these peaks and these valleys. And you should have no heat at all at the nodal plane in here. And so let me show you a picture of what that cardboard would look like after it's been in the microwave. So here's a picture of the cardboard that has already been in the microwave. You can see these black marks right here and here, and they are virtually equidistant from each other. And so the wire that I've placed in here, I've tried just to illustrate for you how the wave goes through. It's at these peaks here and the valleys there that you have the burn marks. Let me show you a quick video of it as well. So this is a little video. Here we have the wire that's just running through the cardboard. You can't see the black marks on there, but you can see where the peaks and the valleys are. And if I turn this on, I should be able to rotate it to be able to see the, there we go. Now we're rotating it to show the places where the hot spots are located. And so to do our measurements, we're going to measure from this black spot there to that black spot there, or from this one to there, and they are roughly the same. We're going to try to find the center, and that corresponds with the peak of the microwave, and then the valley of the microwave, the amplitude's the same on that peak and the valley. But right here in the middle, this nodal plane, there's no burning at all. So we're going to measure this distance from here to here, or technically we could measure the distance from here all the way to there. That would be one wavelength. But we'll just do that from this spot to that spot, and that will give us half of the wavelength, and then we'll multiply it by 2. And if everything goes well, when you measure half that wavelength, you should come up with approximately 4 to maybe 7 centimeters. On the picture that I just showed you, that actually came up to about 8.5 centimeters. Take that, multiply that by 2, and that will give us the length of the entire wave. So we measured from this point to that point, half. So we're going to multiply by 2 to get all the way across. And then we're going to convert that to meters. So we've measured it in centimeters. So let's say that mine came out to 8.5 centimeters. If I convert that to meters, that's going to be 0.085 meters. I take 0.085 meters, multiply that by the frequency, and that should give me the speed of light, because the wavelength times the frequency, when we're talking about electromagnetic radiation, gives us the speed of light, and that's 3.0 times 10 to the 8th meters per second. And that's how we are going to measure the length of a microwave, and then verify that by seeing if we come up, how close we come up to the speed of light. Okay, and that's how we're going to measure the length of a microwave.